here we had calculated the, so far we had calculated the leading contribution to the effective potential, effective action. Now we will calculate the ordered h bar contribution, which we have neglected so far. So that's first quantum correction to effective action. And to do that, we will not we will not go by this path where we follow these 3 steps. There's an easier method of doing it. The easiest way to do it is to directly use this equation to get the result. Let us do that. We know from the leading order analysis that this is true, that phi classical is phi lower bar plus order h bar contribution. So let us begin by writing this down here. Phi local classical is phi lower bar minus h bar times delta. Delta is a ordered h bar contribution to this difference. And then you use that equation, gamma, the Legendre transformation, minus h bar z j plus j prime plus j prime phi cl, and substitute the result minus h bar 1 over h bar lower bar j prime j prime minus half trace log O this is same as action plus half h bar by 2 trace log O plus j prime phi cl. Now I write it in terms of the action, and the explicit j prime dependence is minus phi j prime. This explicit dependence is minus phi j prime. So that will give you j prime times phi cl minus phi, and phi cl minus phi is minus h bar delta. So that will be minus h bar j prime times delta plus h bar by 2 trace log O. Let us now, so this is in phi lower bar. So now write things in terms of phi CL. This phi lower bar is phi CL plus h bar delta. According to this, phi CL plus h bar delta. And then minus h bar j prime delta plus h bar by 2 trace log O. We can replace phi lower bar by phi CL because the difference is higher order in h bar and it is already linear in h bar. So we are calculating only up to linear in h bar. So that within the that's higher order in the in H bar, so we can neglect it. Now we shall what we shall do is Taylor expand this and then keep up to the second term, because that's order H bar, and then and compare that is linear in delta. This is also linear in delta. Compare that two terms. So if you do that, then it is phi CL plus H bar. Let me write this second term first. Trace log O phi CL, then plus. Now I'm writing the second term of the Taylor expansion. So that will be H bar times delta del S phi CL del phi CL minus J prime. Right. So this term I'm getting delta time del S phi CL del phi CL is the second term in the Taylor expansion, and then minus J prime is coming from here. So this is multiplied by order H bar. Now let us calculate this quantity. Let us calculate this. What is this? This is written back in terms of phi lower bar. It is this. Okay. Now this can be calculated as by chain rule. Del is, first let us use chain rule. Del is phi lower bar, then del phi lower bar, del phi lower bar minus H bar delta, where I'm integrating over the location of phi lower bar. Then we got two factors. The second factor can be calculated as del phi CL plus H bar del delta divided by phi del phi CL. Now let me put this argument explicit here. That will be easier now. So suppose this is X, this is a local field, then this is X, and this is integrated Y, and so we are calculating this Y and this at X. So then this is going to be del phi CL Y del phi CL X, that is delta Y minus X, plus H bar del delta Y del phi CLX. This is the result that I would get for the first factor. Now for the second factor, we should use the Taylor expansion of the numerator. So if you do the Taylor expansion, then it is del S phi lower bar del phi lower bar Y minus H bar. There's a Taylor expansion, so delta Z It's getting a little bit difficult to track. Let me do it in more steps and slowly. So this is del phi lower bar y acting on the Taylor expansion of the numerator, which is s phi lower bar minus h bar delta z del s phi lower bar z integration over z. This is what it is, multiplied by this factor, the second factor, which is delta y minus x plus h bar del delta y del phi clx, and integration over y, which is this integration. Okay. Now there are altogether 4 terms. So this derivative is going to act on this and this, and then the 2 terms multiplied with 2 terms. So there will be altogether 4 terms. But only one term among these 4 terms, only one term, which is this first derivative acting on s multiplied with this delta function, is order 1. All the other terms are higher order in h bar, and since this entire term is multiplied by h bar, we neglect the higher order in h bar terms, so we get this equation, this result. Del s del phi lower bar y, but then y integration can be done with the delta function, it becomes x, and then higher order in h bar. Okay, so if we now substitute this result here, we see that this factor can be replaced simply by this factor. This derivative with respect to phi cl of the s classical is same as derivative with respect to phi lower bar of s calculated at phi lower bar, and this is nothing but j prime because of the classical equation of motion. This is same as j prime because of the classical equation of motion. Okay, and therefore this entire term drops out at order h bar. So this does not produce an h bar contribution, it produces a higher order contribution, and therefore the result is basically this. So therefore the final result for the quantum corrected effective action is phi cl minus h bar over 2 trace log O phi cl. That's the result. Now this trace log O, which we wrote by replacing the determinant O factor, and also determinant O was obtained by formally using the Gaussian integral result of countable degrees of freedom. So let us have a look at this, how we could manipulate this part. So this is nothing but so what one can do is, so this is basically trace log minus del squared plus m squared plus v double prime phi cl. So earlier we wrote a delta function, delta x1 minus x2. Okay, let me explain my notation here. So earlier O was written in this way. Here. So this is the expression for O. So this is the differential operator, and this is delta x1 minus x2. So O viewed as a matrix operator, it's a differential operator, but it's we are here in this, while after obtaining doing the Gaussian integral, we view it as a matrix. except that the matrix, the two indices are continuous indices. These are x1 and x2. What this factor tells us that it is a diagonal matrix, because when x1 and x2 are different, these are the two legs of a matrix. When they are different, then it's 0. So this is a diagonal matrix, and the diagonal element is this one, which is a differential operator. This is what the matrix is. Now, what we are going to do for this manipulation in the other page, I'm going to get back. I'm going to remove these from this notation, but view these as some general matrix operator, an operator which has two legs and can be differential operator. But the fact that it is a diagonal operator and the diagonal element is this particular differential operator will be used later after doing certain manipulation. So I'm just using the symbol, this one, not this one, to represent this, symbolically represent this entire matrix operator, for the sake of doing certain manipulations. So that is what I just said. Let me repeat. This is an operator. Meaning of this operator is that this operator is a matrix operator with two indices which are continuous. This is a diagonal operator, and the diagonal element is given by this differential operator, where the derivative with respect to the diagonal index, which is x, and this one also has to be calculated at phi CLx for the xth diagonal element of that operator. This is what it is, but now we symbolically use this as an arbitrary operator with the description that I said kept in mind. If you do that, then we know we can do this. It is like x and say x and this one is say u. Okay, so then it is like trace log x plus u. This can be written as trace log x times 1 plus x inverse u. That is trace log x plus trace log 1 plus x inverse u. And this log 1 plus x inverse u has a power series expansion, which is given by sum over n equal to 1 to infinity logarithmic expansion minus 1 to n plus 1 trace log x inverse u. Sorry, that's not right. This is trace of, so trace of this x inverse u to the power n. Now the trace log x, this part, which is trace log minus del squared plus m square, is phi CL independent and therefore a constant piece. Phi CL independent. Constant. And therefore we can drop it from the effective action. If we do, then we are left with this term. So gamma phi CL is equal to S phi CL, then minus, sorry, this is going to be, this was I think plus h bar by 2. Yeah, this will be plus h bar by 2. And then this logarithmic expansion. So plus h bar by 2 inside, say n equal to 1 is trace x inverse u minus, I think there is a, just a moment. Next one, so there'll be a 1 over n in the logarithmic expansion. That was a mistake that I made, and then minus half trace x inverse u square, and so on. All this in whole infinite series is only at h bar, at order h bar. Now let us look at these two terms in terms of these operators. So trace, let me write it separately. Trace x inverse u is what? What is x? X is the differential operator minus del square plus m, and x inverse must be a Green's function. This is a Green's function, and let me define it here. So define Green's function to be minus del squared plus m squared acting on delta c x minus y is equal to delta x minus y. So it is in this sense, delta c is the inverse of this, and u is basically v double prime of phi CL. So when you say trace, we have dx x inverse so x inverse, say x y u y x, this y has to be integrated, and because of the trace x has to be integrated. Now x inverse xy means delta c x minus y, and u y x is basically, u is a diagonal matrix whose matrix element is v double prime phi CL at that point. So it is v double prime phi CL x times delta x minus y. Okay, so that is the result. And then trace x inverse u square means trace x inverse u which means that x inverse xy u y z x inverse z u x. That is the, and then you have to integrate over all of them. So that is integral dx dy dz du, dx dy dz du delta c x minus y. This is v double prime phi CL z delta y minus z, that is u y z, then delta c x inverse z u is z minus u, and v double prime phi cl x delta u minus x. So this can be sum of the integrals. How many integrals? There are two deltas. So if I integrate over y and then delta c x minus y is same as z, v double prime phi cl z. C z minus u, v double prime phi cl u delta u minus x. This is what it is. You could also integrate u, that will give you dx dz delta c x minus z v double prime phi c z delta c z minus x v double prime phi cl x. That's it. So so that is how the effective action is going to look like. This classical action plus order h bar contribution, which has this series of terms, and this can be calculated this way using the Green's function here. Okay. Now we have done so far what we have done here is that calculated gamma up to order h bar, but then we had used an indirect argument which should be and the explicit the actual algorithm mentioned here, which is basically this claim. It must be valid claim, it must be true, and one should be able to verify that explicitly. So let me just pose this question of a verification. So one has to show that del del j of s phi lower bar j comma j is equal to phi lower bar j. This is one has to show given that s phi j is half del mu phi plus half m squared phi squared plus v phi minus j phi. And del s del phi at phi lower bar, which is given by minus del squared phi lower bar plus m squared phi lower bar plus v prime phi lower bar minus j equal to 0. So I have already posed the problem earlier. Let me repeat it again. So this is the action and this is the equation of motion, and the solution is phi lower bar. This solution, this can be solved in using the Green's function method, where the Green's function is given by this delta C here. Using that Green's function, you can solve phi lower bar as a functional of J. Substitute that functional here back into that this action to calculate this entire thing, S of phi lower bar as a function of J comma J, and then take derivative with respect to J and show that you get back the same phi of J. So whatever you get here is a functional of J, and then replace J by its inverse relation, which is given nothing other than this. So J is equal to this. So if you replace in this expression, after you get this and they take derivative and then replace J by this, you should get back this. This is what one has to show. That would be required for consistency of what we have done. There's some further studies that one should do, is which I'm not going to include in my lectures here. So it is possible to calculate the entire all the terms of the effective action when we consider the effective potential, which is basically can be calculated by calculating the effective action for a constant field configuration, which is given by V phi CL plus H bar U phi CL plus order H bar square. This is called the Coleman Weinberg potential, that H bar order potential. So this can be obtained by evaluating the functional determinant for a constant field configuration using zeta function method, which uses heat kernel technique. I will not be able to review it here in these lectures. This has been reviewed in detail in the Ramon's book.